Hello and welcome. This is the eBPF and Cilium Office Hours live stream, also known as eCHO. We are at episode 195. Now, I'm just going to have to do something about my audio because I'm getting a weird echo. So let's see whether I can fix that before. I might just have to deal with a strange echo the whole way through the show. It'll be fine. So welcome to this episode. I'm going to introduce my wonderful guest, Dylan, very shortly. But before we get to that, I have one big ask for you. This week, please fill in the Cilium user survey. It will only take you a few minutes. It will really help the project to understand how Cilium is being used and what's most important to you moving forward. So if you can, click on the link in the show notes on HackMD. There's this link to Cilium user survey. Spend a few minutes on that after the show today. That would be wonderful. As always, please do say hello. Let us know where you're watching from. I have an unusual background today. I'm actually doing the live stream today from Mallorca. So that's hence the change of environment today. All right, I think it is time to start talking about the topic for today, which is making Cilium Clang-free. So let me introduce my colleague, Dylan. So welcome, Dylan. How's it going?
Hey, everything all right? Thanks for having me on.
Always a pleasure to have you here. You've been a repeat guest on eCHO, and you've always got really interesting things to say here. So I think this is going to be a really interesting show. So just to set the scene for the audience, we had a what we call a hive time, like a sort of engineering conference for the Isovalent team about a month ago, I guess now. And one of the topics that I attended was a talk about making Cilium Clang-free. And I thought it was so interesting, we had to bring it to the rest of the world, show it on eCHO. So welcome, Dylan. You've been working on making Cilium Clang-free, making it runtime configurable. So maybe we can just talk a little bit about the sort of history behind this, like what's the current situation and why do we ship the Clang compiler as part of the Cilium agent?
Yeah, so the whole, I guess the whole idea of Clang freedom, as we call it, started about 2 years ago when we realized it's actually starting to become a possibility for us. The Cilium project itself is really old. I believe I just looked at it and first committed 9 years ago by
I think we're going to have a big celebration next year for the 10-year anniversary.
Yeah, exactly. But of course, like 9 years ago, eBPF was a way different capabilities, way more constrained, and it just looked different. So project is really old and really grew like side by side with eBPF. And so especially until I believe 4 or 5 years ago, it was really normal to do compilation on your target. So you would have a project like Cilium, and you take all of the C code, all of the header files, everything that is the eBPF code, and you ship it together with your project. That was the norm for a very long time. And there's the BCC project, for example, which does this with Python. So you have your C code inside of your Python project, and it compiles it on the go. And there's very good reasons to do it like that. So for us, most of that came down to a constrained environment. So Cilium has a lot of features, and a lot of them are optional. You can toggle them on, off, or set limits on them, which every feature you implement in eBPF has a certain cost to it. The verifier has this thing called a verifier complexity limit, where if a program is too big or does too much in a number of senses, then it's too big to guarantee it's safe within a reasonable amount of time. So,
and I think anyone who's spent any time writing eBPF code will probably have hit that verifier limit at some point. So yeah, it's a familiar problem. Even though it's now like 1 million instructions, it's still not hard to hit it.
It's if you make a small mistake, or you don't watch what your like the amount of complexity you have, it's very easy to hit it. And it used to be 4K instructions, so we wouldn't be able to allowed to have more than about 4,000. What is it for? Yeah, about 4,000 instructions. If you went over it, just no go. So we had to be really careful with how much instructions we had, and also even after the limit is raised, we don't want to have users pay for features they don't use. So even if we make it past the verifier, if every feature you enable is still code that has to run for every packet or every time something happens. So we very strongly believe in this model of only pay for what you use. That is in memory, it is in CPU, it's also verifier complexity in this case. So our whole code base is filled with these toggles where it's like, if this feature is enabled, then we include this bit of code, and if it's not enabled, we don't. And that this has worked. It still sort of works, but it's not ideal because we have to ship Clang, which is really big actually. It's easy. I believe it's like 50 megabytes of just binaries, like all of the libraries that it depends on the static binary. The whole toolchain is big, and we have to ship all of our source code, which is very unusual for projects where you can normally just pre-compile something.
I mean, I guess we only ship the source code for the eBPF programs inside the agent. We don't ship the whole user space code as well, but yeah, point taken. You have to, yeah.
But the source code is much bigger than the actual binary would end up being, because human readable instructions or human readable code is way bigger than your instructions.
And from a security point of view, we absolutely want to remove anything from an image that isn't necessary, because the less code there is, the less chance of some kind of vulnerability, some kind of exploitable vulnerability inside that image. So we love the idea of making images smaller.
Yeah, and it's like it's pretty much industry standard to have either distro-less images or images with very narrow, like the very minimal images with just the basics in there. That has been the standard in Kubernetes for years now, and we've just not been able to do it because of our dependency on a lot of these runtime tools.
Yeah. So before we move on to how we're approaching fixing this, I just want to very quickly say hello to Tony and also to Joseph. Always good to see our regular viewers. Hi. Right. So I think we understand the problem. Now maybe we can. And we've also got Mahe saying hello. Hi. Great. Okay. So we want to be able to remove Clang from the image, and we want to be able to avoid having to recompile eBPF programs every time we change configuration, or for each different configuration. Joseph is asking where my drums and so on are. So Joseph, I'm actually speaking to you from Mallorca, so I didn't bring my drum kit with me. All right. So should we maybe think a little bit about like the how we've previously done the build time configuration with like hash if defs in the code, and how we want to change that into something runtime instead.
Yeah. So what I was describing, like these feature toggles, they are all preprocessor statements. So if for anyone who worked with C, there are these hashtag statements where you can say if def for to see if some macro is defined or not, and then conditionally compile it. And I guess it's easier if I show my screen. So I made a little example to show this off.
Wonderful.
So what I did is I made a little example program. So this program is something I just came up with like an hour ago. What it does is it's just a little neat example program. It's a traffic control program, so the same sort of program that Cilium uses predominantly. And what it does is I made a little filter which which looks at the IP or the IP protocol, so like TCP, UDP, whatever protocol there is, and then you can have a filter that would drop a packet if you don't want that particular type of traffic. It's not. Okay. It's a construed example, but I just needed something to show, and then I also made a second toggle which would add metrics to this. So it's just a counter. So every time a packet would go through this, it would count up. But this sort of reflects the way we would write code in Cilium, where we have some enable underscore macro, which for the sake of this example I just put here. But in our case, so for Cilium, we tend to generate separate header files where we on the fly generate these defines, and that is how the project basically always has been passing load time configuration into Cilium. So you generate a bunch of files with these defines in them. And then in our code we can use them and say, okay, if this feature is defined, we compile in all of this, and if it's not, then it's not there, and you can, for all intents and purposes, like this block of code is just commented out. So that is how our usual way of writing this. But we want to get rid of it. So what newer kernels, so kernels 5.5 and above, allow you to do is to actually use global variables for this. So instead of having these
global variables in eBPF.
Yeah, exactly. Yeah. Well, so global variables in eBPF were a thing for longer, but what is specifically what the verifier specifically is able to do is we can tell the verifier that a global variable is actually static. It's not going to change during the lifetime of a program. So and before 5.5, you were able to create global variables, but the verifier would always assume like, oh, this might change at some point. With this capability, which I'll demonstrate what it actually does at the byte level, the bytecode level. But the way you use it is actually very straightforward. You create a variable. So I created a Boolean here for my two enables. But this works with things like IP addresses, MAC addresses, and more complex things as well. We tell it that it's a constant. So this is important to. This is mostly important for the loader. So it will actually see, oh, this is a global or a global constant variable, and it will specially mark it so that the verifier understands that it's a constant as well. And then which something that's somewhat interesting is we also have to mark it volatile. And volatile in C means that the compiler may not assume anything. So it cannot make compilation time assumptions about what the value of this is, because we assigned it false here. So if we wouldn't have this volatile here, the compiler might just compile out our whole branch, which we don't want to. We still want to keep everything there, and we want to defer this decision to the load time, right?
I feel like that's an interesting, like, why would we want to not let the compiler remove the code? Why do we want the loader to make that decision?
So the difference the difference that we want to achieve is we don't want to do compilation on our target machine anymore. So what happens is when you compile. So actually, I have the make file here. So when we compile a BPF program, this is the simplest way to do it. So you have I have my C file, and it does include some header files. But I say, okay, I want to take my C file and I want to compile it into an object file. And we have to pass in some other flags for optimization and to tell it that it actually should compile it into BPF. And then our output is this .o file, and our .o file actually contains that's not the. I have to do object dump. That's what I want.
I was thinking BPF tools grown since I last looked.
No. I also wanted to show something later on with BPF tools, so my mind was still on that.
Yeah.
If I can actually object dump is the one that I wanted to show off. So our you get this object file, and this object file actually contains our BPF instructions. So it's what is called a relocatable ELF file. So it's not executable like a normal binary might be. And it contains a bunch of meta information and so on. But this is what we normally deal with at the loader level. So the compiler gives us this binary file, and then the loader can do stuff with it. And the current way we do it is we do this all on the target. So we go from C to object file to loading it all at runtime when we want to load a program. But now what we want to do is we want to have this object file be created in our continuous integration environment. And then when we are about to do a Cilium release, we will have these object files be created just like our binaries in CI, and then that is bundled. So we would ship these O files either internally in our main binary or as a separate file for separate files. But every possibility that we want to be able to toggle at load time, we want to have in this object file.
Right. So we need all of the code for all of the different options to be in that object file. Yeah. And then at load time, we're going to maybe pick and choose some pieces that we don't need.
Exactly. And conceptually, it looks very similar to the legacy, right? Except for instead of having an if-def here, we're going to have a normal if statement. Right. And now, normally, if you would do this, if you would have this, you might need to pay for that, right? So the verifier, if this were any normal variable or not a global constant, then the verifier would have to consider this bit of the code and say, okay, at like every time you run this program, it might take this branch or it might not. So you have this branching instruction, which is even if it's always true or always false, having a branching instruction causes slowdown on the CPU. We have a big program, like a big amount of instructions that might not be reachable, which take up space in your instruction cache on the CPU. So this is, at first glance, this is not a one-to-one replacement for what we were doing. But the cool thing is what I was talking about in 5.5 is the verifier recognizes that these are unchangeable, and it can actually optimize for that while we are loading. So on the Go side of this, I wrote this little loader program to show this off. So I took our variables and I made flags for them as in my program. I told the Cilium eBPF library, which does all of the heavy lifting here of like interpreting the bytes and just gives us something to work with. So I'm going to load our object file. I will print out what the instructions look like, sort of like what I already showed with the object dump. And then we get access to these variables. So we call these the variable spec API. And we can actually set, so we can now change these variables right before we load them. So we have this step where we interpret the object file, we can make some changes, and then we actually load it into the kernel. And then after I loaded it, I'm actually going to look again at the instructions, but this will reflect the actual instructions that were that the kernel has turned this into. So I do have to run this as sudo because I need some. I'm in the wrong directory because I need a root permission to load my BPF program. And what we will see is by default is we have these instructions, and here's, for example, the first if statement. So the first thing we do is we have our if statement. We load our if statement from the RO data, so the read-only data, and then we compare it with we see, do we have this setting set to true? So in the object file, what the compiler gives us is just the full program, just as you might expect it works. And then currently I have enabled both features. So you'll see that we load the same amount of instructions. So we had 40, actually we load a little bit more instructions. So I can explain this actually. So the verifier doesn't just verify, it also does some optimization work. In this case, what it does is I have a, let me see where I have it. We do a lookup in the filter map and in the metrics map, and verifier will actually inline these functions for us. So in this case, it actually, so here we can see we have a lookup, but it doesn't have a call instruction anymore. It just made it into a lot of inline instructions. So it actually, the verifier is already doing a lot of work to help us out with performance, which is why we have a little bit more instructions here. But my point was we don't have less.
Yeah.
So what we can actually do now is I can, for example, say let's disable the filter, and if I load it now, you can see that there's only 26 instructions remaining, but I still loaded the same 41 instructions. So I gave the kernel 41 instructions. I changed the global variable. And the kernel is actually able to recognize, okay, that means that there's a bunch of code that is never going to be reachable, and I can just leave it out. And I can do the same for the metrics. And if we do both, we actually end up with an empty program, right? So I have the two if statements, and if I were to collapse those, then the only thing that happens is we just say, okay, let this packet pass, and the only artifact we can see here is it still says if enabled filter, if metrics is enabled. So what the verifier does is it eliminates the branching instruction and the content of the branch, but it still has these two instructions where it's actually still loading the value, where it's still loading the constant value, but it doesn't do anything with it anymore. So there's a little bit of overhead, but it's like two instructions that are basically that are not very expensive. So this is pretty powerful, because now we can pre-compile all of our code, and we can write it. We can a programmer can write it as they would normally, but they do not pay any cost for this. So it's not it's optimization, not in a compiler, but at the loader stage. And this I think this capability is the reason we can do this is why we can go Clang freedom, why we can do this at all. So it's
that's
to
really
me this
cool.
is really exciting, right?
So if we translate the example to something more in the sort of Cilium world, the Cilium user space component is going to look at the configuration that it's been set in, let's say, the Helm chart, and it's going to use that configuration to enable or disable certain features in the eBPF programs and load those programs.
And I can actually show it off, because we've already started implementing this a little bit. I picked this specifically. We have quite a few places already, but this let me see, when did 4 months ago this was added. So it's a feature that extends that allows passing of IP protocols. So actually not too dissimilar to the example I had created, but it looks slightly different, and I'll go into why that is in Cilium, because we wanted a little bit more advanced functionality. So we built some tooling around it, but the concept is the same. This is a global constant variable. It's a Boolean. We gave it a name and we gave it a description, so we know what it actually does. And if I go look where it's used, we have the same pattern of usage, where we say, okay, I have an if statement, and here I can just say I want the config value of this variable. So we did add a little bit of fluff around it, but the concept is very similar. So at load time, this branch is enabled or disabled, and it's a very small thing here. You can see we still have a bunch of if-defs around it, which is because we're still in the process of slowly moving from one to the other. But this is how an eBPF or a data path developer would use it. I noted on the little bit of fluff. So we, as the loader team, created this little abstraction. So it's still a volatile const, but we added some additional information for ourselves. So we put our all of our config in a dedicated section, which is easier for us to work with, and we give it some metadata information. So we can actually tell it that this is configuration that is very specific to the object, and this description that I alluded to earlier. The other way is we have this the secondary way to configure it, where we say this is a kind node, and the reason we have this is because of a very Cilium specific reason, which is we have a lot of programs. So we have host programs, LXC programs, network overlay. So we have a bunch of these different programs that we attach on different locations on different devices. And our node config allows us to create config that is node-wide. So you declare it once, and it gets applied to all the programs that you're going to load. And if you have the normal one, you can have configuration that is very specific to an LXC program type, for example. Okay. So, and then for us, a little bit of what we find important is that we can work with native types. So we have so what we do is we generate these, or in CI we have the we have all of our big collections, like our big collections of programs. And per collection, we can actually generate a Go structure that reflects all of the defined configuration for a given program. So this gets generated by a little tool we call dpgen, and we turn all of these definitions into a single Golang struct and with native Go types. And then for individual things like booleans or numbers, they're just translated into the Go equivalent. And for things like MAC addresses or IPv4, IPv6 addresses, they're just byte slices, which we can populate. We also have the default values, which are defined here. And then when we use it, so this is the loader, the loader bit. We can just pass this configuration object. So what we do is we have in Go, we have the local node configuration. So it's like the configuration of Cilium, the whole node. We turn that into the node-wide config. So we have one conversion function for that. And then for XDP specific features, we can just assign them. So this option config comes directly from our flag values and from our Helm configuration. So we can one-to-one, sort of like the example I already showed, we can define flags or Helm values, and we can pass them pretty much one-to-one into our program. And then our tooling takes care of making sure that this gets communicated properly to this global variable.
Okay.
So on the Cilium side, it's simpler, but a little bit more feature. We added a little bit more comfort features for ourselves.
Very nice. And I think we'll talk in a little while about what other, if other projects want to take a similar approach. But before we go to that, I think it's pretty clear that there is work to be done to kind of I don't want to say rewrite, a sort of small refactor for BPF programs that need to use these runtime configuration settings rather than, replacing the hash ifs that are currently there. That I think is ongoing work, right? Or is that?
Yeah.
That's ongoing. But
you
aside from that,
crawl through any arbitrary program, and there is we'll have a bunch of ifs left. So that is just a matter of converting these over. So that's going to be refactoring, but like I pointed out earlier, the structure of the code is very similar. So this will probably just become an if statement, and the code is pretty much structured the same way. We have a few challenges still. So one of them. So we
actually before we go to that, let's just quickly answer Mahe's question. He's asked if we can show again how you change the name of the frozen map that will contain the values from the C or eBPF point of view.
Right.
I saw the name. Eagle-eyed spotted read-only data.config rather than the default.
Exactly.
Read-only data.
So it's actually very similar to the way you define the location of a program. So when you write a program, you always have to tell it what the program type is by using this SEC macro, which stands for section. And for maps, we use the same macro, and what we simply do is we take this. So in Cilium, we call it underscore section. It's the same thing. We just have our own name for it. But if you go look at, it's still attribute section, and here as well, it translates to attribute section. So we use the same macro you normally use to place a program in a specific section or a map in its section, and we use it for every configuration variable to place it into the read-only configuration section, so that it's so that the values we want to be able to change at load time are in a distinct place from actual read-only values, so that we would never change at load time.
Great.
I hope that
thanks.
answers the question.
I think so. Mahi can tell us if he has a follow-on question. You were going to talk about the sort of additional work to
Right.
that still needs to be done and the remaining complexities.
So yeah, actually one of the things that we actually very recently solved, and that was also a big point of the internal Hive time discussion, is what to do with maps. Because so I going back to my simplified example, I have these two maps here, right, where I have a matrix map and a filter map. And what turns out to be the case is that the way the verifier works, at least currently, is that when you load a program, there's an association between a program and a map. So so that as long as a map lives, or as long as a program lives, it keeps a map alive, which makes sense, right? You don't want the map to go away while you still need it. The only thing is that it doesn't take into account our dead code. So if I were to print out the maps that are associated with my program, and I run it normally, you can see that I have 3 maps. The first one being our read-only data, and then the 2 other maps would be our metrics and our filter map. And if I load without them, I don't use them in my code, but I'm still referencing them. So I still need my maps to. I still need to create these maps, and you still need to pay a memory penalty for them, at least by default. As long as even if I've disabled the feature that belongs with it. And the way we used to deal with this in the legacy world was to simply surround our map definitions with if-defs as well, which circumvents that issue. But we can't do this with load time. And if I were to remove my maps from my definition, then my program doesn't load. So even if my code is dynamically dead, the verifier still enforces that this is that there's actually a map for it. So we had to do some work to get around this in Cilium. So what we ended up doing is to implement what we call reachability analysis, and for that I'll actually go to the slide deck which I have prepared for the presentation. So I took a little bit of code to explain the same thing. So the old school way of writing this would be an if-def, but in a new way we write it. We want to do this. We want to have our map without anything around it, and then depending on how we use it, we want to eliminate it. Now, what turns out to happen is that you can actually recognize our own load time configuration. So we have our if config on the right, and this translates into 3 instructions that we could also see in the example before, where we load the pointer to our map, to our read-only data. We read the variable at a specific offset from it, and then we do a comparison. So what we did is we wrote some code to analyze our bytecode in user space before we actually give it to the kernel, so we can determine before we even load it which parts of the bytecode would be reachable or not reachable. In this case, if this value or if this feature would be disabled, we would skip over this full map, so we know that we don't need it. And what we then do is we actually blank out this map pointer. So we call this it's something we call poisoning. So we make this into code that doesn't. So if the verifier sees this, it doesn't recognize it as a map being referenced, but it just thinks it's some random value. And if the verifier were to actually try to verify this, it would of course fail. But because we know that it's that code, we can poison the instruction like this. We will no longer need to provide the map reference. We can basically we can load our program, only poison these single instructions, and then not have to deal with the same ref counting issue where we hold on to maps, or we need maps that we are not using.
So that means the verifier is going to, well, actually, is it the verifier, or is it actually at runtime that is going to keep the reference count to the maps? Well, it's a 0 reference count, so the map doesn't need to be created.
Yeah. So it does. It's two things. It's the first is we don't have to actually create the map in the first place, so we save a lot of churn of. So even if the verifier were to be smart enough to release the ref count after verification, we would still have to create it initially and give it to it, right? But now, because we know at load time which maps we will and not will use and will not use, we don't have to spend time and effort in creating these maps. So it saves a lot of resources during map creation.
Okay.
And we actually extended this. So this is a little bit of static analysis and logic we had to implement to basically get on the same level of performance as we would have with compilation on the go. And we extended the same principle for us to do tail calls. So we liberally use tail calls to have more to be able to make bigger programs in Cilium. And we actually took the same logic and we applied it to tail calls. So we can now write logic like this, where we say, okay, we conditionally do a tail call, and if we know we are never, don't don't show it. But if we know we are never going to go into some tail call, we can actually completely remove it. So normally you would have to load every tail call. Now we can just say, okay, hey, we know that the tail call for full feature is never gonna get used, so we can just not load it and not put it in our tail call map. And we can that way we can save a lot of resources when loading to avoid that. So we're trying to apply these. We wrote a bunch of tooling for this to add some more smartness on top of what the verifier already does.
Speaking of the word smart, Mahe has described this approach as so smart. So in Tetragon, they resize maps to a size of 1 before loading to reduce the memory use, but you still end up having the map created, and there's a limit apparently of 64. I didn't know the limit was 64, but there we go. But if you don't create the map at all, you don't have to worry about that limit. So I think that's a really interesting point. And maybe that kind of brings us on to the idea of, well, what if other projects want to take a similar approach to this work that we've been doing in Cilium? How can other projects do something similar?
So the whole using global variables is not something that's unique to Cilium. For example, in Cilium eBPF, so we did a lot of the custom tooling around it that I showed off, right? In the Cilium eBPF library, we have a thing called BPF to go, which already helps a lot with this. So what it does it does a version of this. So if I invoke it, it can generate Go scaffolding for you as well. And what this Go scaffolding does, among others, is it already gives you these neat generated structures where it basically does the same thing. So you can just it doesn't give you the exact Go type. It gives you the variable spec. So it's slightly less convenient than what we did in Cilium, but this already exists. C users, so people that use libbpf, have a similar thing, which is called a skeleton. So this was the BPF tool bit that I actually wanted to show off. So you can create what is called a skeleton. You can do the same thing. So it generates a C program, and the C program will actually have these global variables in there as well. So it's sort of the same concept where you can say, okay, load my skeleton, and then you can just provide it the C variables as well. So this bit of the this bit is quite universal. I don't think so. As far as I know, IARS, so the Rust loader library that's most popular, does have a feature that is similar to our variable spec API, so very similar to this. But I don't think they have skeletons yet, to the best of my knowledge. But it's also you can probably do something very similar there. So the global variables are pretty much universal. I think what is still special sauce is this reachability analysis that I've been talking about. However, it is public. This is just in our Cilium eBPF repo. So we have this Go package which is called BPF, and it has all of the code that does the reachability analysis and all of the logic. So for now, until we package this in such a way that it would be more reusable, people can just copy this out or use it with a few quirks directly. Because
was there a reason why this is part of the Cilium project, Cilium, and not part of the eBPF Go library?
So yeah, well, it is currently part of Cilium because Cilium eBPF, we are a little bit more cagey on what we want to have there. Because if we have it in Cilium eBPF, we want to be truly universal. And we felt that this was still a bit Cilium specific. At least when we were developing on it, working on it. And also, we would probably want to provide this in a separate repository or additional to Cilium eBPF, because there's no reason why it would have to live inside the actual shared Cilium eBPF code. Other than this might be really useful for some people. So yeah, I think we're open to doing something with this in future, but currently we haven't done so yet.
So I guess if somebody's watching this and thinking they would like to be able to incorporate this into their eBPF project, probably the best thing to do would be reach out on Slack and start figuring out. I mean, obviously, as you say, they can just take this, copy it, do whatever they want with it. But longer term, it would be nice to have a common package to do it.
Especially for Go, because for Go, there will be no reason to duplicate this. If you are a C user, so you write your loader in C as well, there is very little choice other than to basically rewrite it in C based on what we've done. But yeah, we're definitely, I think we're open to perhaps pulling this out into something that's useful for more projects. Because it's definitely a neat thing to have.
For sure. We're coming up to, we've got just less than 10 minutes before the end of the show. So if anyone is watching and thinking up a question, now would be a really good time to type it in. And we do love your questions. Mahe has made the point that importing Cilium in a Go project would be a lot. I mean, obviously the entirety of Cilium is a lot of code. You probably don't want that in every eBPF project.
Very true.
So I think that will be a nice potential thing that might happen in the future.
Yeah, I did not fully answer your question because you were asking about future challenges, and this is recently fixed challenges because this is like we're talking changes that happened like weeks ago. So I guess the last little bits, other than actually doing the work of migrating, are maps. So one of the things that we currently have is now I need to find it, and this is the bit that I hadn't prepped yet. We have a lot of maps somewhere where actually I'm just gonna cheat. So if I, for example, go, and that is exactly not what I needed, max entries. So let's take this one. So this map is this is a XDP specific map, but what you'll see here is that the actual definition of this map contains preprocessor statements. In this case, the max entries is the only thing that's actually truly dynamic. So the way Cilium currently works is we have these we change the size of our maps via the compiler. So if I were to look this up, then we have some we have defaults in the dummy header just so we can compile. But we actually normally we render these out as header files based on Go values. So here they happen to be very static, which so they're actually bigger here than normal, than we have in the dummy file. But these are also some of our maps are actually like resizable with flags and or dynamically with memory budgets. And this is something we still have to figure out. Well, actually, we know what we want to do, but we still have to actually do it. Where we want to move this resizing logic to be fully in user space and not go via the compilation step, because it's the very last thing I think that currently would hold us back from moving. So it's this, and we have now the question is if I can find this. We have a few interesting bits left and right where we have what we have, for example, is this VLAN filter, where what you'll notice is this VLAN filter is actually a function. So what the way this works in our code today is that this VLAN filter is actually generated. Oh, now that I found it, I need to go to the Go codes. So this VLAN filter is actually a bit of preprocessor that gets generated in. Here it is. It actually gets generated in Go. So there's this like preprocessor logic that we render out, and we need to. This is going to be more challenging to convert over. So it's definitely possible, but we have to like change these. We have to take care of these more complex things that we did with preprocessor statements and convert them over to. So we are able to actually do the ahead of time compilation. We have like a handful of these, so it's not insurmountable, but those are currently the only like the things we have to start looking at.
Right, and we have to get all of those dealt with before Cilium can become Clang-free.
Yeah. So this is going to take, it's just going to take some time, but hopefully, like if you don't pay attention to it for like a few months or perhaps a year or so, hopefully someday we might see in the release notes that we're now finally Clang-free.
That'll be another big celebration. That'll be great.
That would be huge.
Tony made the point earlier on that it will speed up deployments, which I think that's true. We won't have to wait for compilation. It's as we're loading Cilium, so that is very true. Madhavan said hello earlier on, and I missed it earlier, so hi, Madhavan. And I think with that, just before the end of the hour, unless there's anything else, Dylan, that we meant to cover and we've missed.
I think we covered everything.
Covered everything. Yeah, fantastic. Well, I think it's absolutely fascinating, and I'm really it'll be a big party when we get rid of Clang. I think that'll be. And I don't mean that, no offense to Clang. We just don't want to carry Clang with us everywhere we go.
We're still gonna use Clang a lot, but during development and during release, like building ahead of time, we're no longer taking it with us when we go into Docker images.
Absolutely, it can live at home in the CI/CD pipeline. Wonderful.
Exactly.
All right. Well, Dylan, thank you so much for another really interesting eCHO episode, and thanks to everyone who's been watching. Thank you for your questions and comments, and we'll see you again very soon. Bye for now.